Okay, we're going to go ahead and get started on section 9.5. I'm going to be making 10-minute videos, and then I'll probably stop and continue on from there. So, we're going to worry about now looking at endpoints in an interval of convergence, so we can figure out whether or not to include those endpoints when we are determining convergence. So the first bullet point, the area-based convergence test that we found on page 92 is known as the integral test. So that was the little exercise where we looked at the results from the ratio test of 1 over n and 1 over n squared, where we found that the ratio test gave us both 1, which was inconclusive. And then we followed up with using what we learned in chapter 8, where we looked at an indefinite integral and the p-series, what we knew about the p-series, and we found that 1 over n diverged, but because the exponent was greater than 1 in case 2, we found out that this one converged. So more formally, we brings about what we're calling theorem 10, the integral test. Let a sub n be a positive sequence of terms. A sub n is some function of n. In other words, we take this and we write it as a function. F is continuous, positive, decreasing for all x. Then the series and the integral either both converge or both diverge. So clearly this is a very powerful theorem that we're going to be able to use to solve our problems. So in other words, applying the theorem, if the integral from 1 to infinity of 5 over n plus 1 dn converges, then the series will converge as well. So we're going to go ahead and try to solve this integral, 5 over n plus 1 dn. And if you recall from chapter 8, the first step is to replace this infinity with a letter. So we're going to say take the limit as b goes to infinity, 1 to b, 5 over n plus 1 dn. We should know how to integrate this, and clearly you should come up with the natural 5 times the natural log of n plus 1. And we're going to evaluate that from 1 to b. So we're going to pull the 5 out front and then take the limit as b tends to infinity of the natural log of b plus 1 minus the natural log of 2. Now the natural log of 2 is a number. It's pretty small, but here we're trying to take the natural log of infinity plus 1. So clearly this is going to infinity. So our solution, taking 5 times infinity, is going to end up giving us infinity, which is not a number. So we end up saying that we're divergent. So our conclusion is that since the integral from 1 to infinity, 5 over n plus 1 dn, diverges, then so does the summation of n equals 1 to infinity, 5 over n plus 1 by the integral test. So the integral test is a good go-to if you find out that the ratio test is inconclusive. Near the bottom of the page again is our review of a p-series written in the form 1 over n to the p. When p is 1, we call this the harmonic series, and we saw that on the previous page. And it is a divergent series. So in general, we can conclude when the exponent p is bigger than 1, we converge, but when it's less than 1 or equal to 1, we diverge. Moving on to page 10, this test should sound a little bit familiar to you. This is the LCT, the limit comparison test. So we're going to look at that one first, and then we'll continue on to the alternating series test. So this works like it did in chapter 8. If I have a given series a sub n and it's greater than 0, and I come up with, this is mine to determine, come up with the b sub n, and I know they're both positive all the time for all n. If I take the limit of a sub n over b sub n, and I get a number, and that number is between 0 and infinity, then what we can conclude from the LCT test is that then A sub n and B sub n either both converge or they both diverge. It's on the next line, but I'll just go ahead and write it in. So you have to know whether B sub n is convergent or divergent when you're picking it. Now, if I take the limit of A sub n over B sub n and it's 0, and B sub n converges, then A sub n also converges. Or if I take the limit and it's equal to infinity, and I know that B sub n diverges, then A sub n diverges as well. So let's go ahead and start some of these sample problems. So the first one says, to determine whether the series converges or diverges using the LCT. So I'm going to start similar to how I've done some of these other ones, where I'm just putting in a few terms. So the first term would be 3 over 4 plus 5 over 9 plus 7 over 16. So just by looking at these values as n is growing, these values are actually decreasing. So I'm going, and based on what I see here, the highest power here and the highest power here, if I simplify in my head, I think 1 over n would be a good series to pick for B sub n. So I'm going to let B sub n equals 1 to infinity 1 over n, which is a known divergent series. So I'm going to go ahead and run this limit as n goes to infinity, A sub n over B sub n. So that's the limit of 2n plus 1 over n plus 1 squared over 1 over n. Flip the guy, so n goes to the numerator. So I have n times 2n plus 1 all over n plus 1 squared. So I'm going to distribute the n. N goes to infinity, 2n squared plus n, and then n squared plus 2n plus 1. So if I try to take this limit, I get infinity over infinity, so I have to run L'Hopital. I take the derivative, I get 4n plus 1 over 2n plus 2. Taking the limit, again I get infinity over infinity. So I'm going to do L'Hopital again. And when I do that, I get 4 over 2. I get a 2. So this is case 1, and 2 is actually RC. So I have 0 less than 2 is less than infinity. So I either both converge or both diverge. So since B sub n diverges, then A sub n also diverges by LCT. I actually like this one more than I have in the past. So I'm going to go ahead and stop this video here and restart with the next example.